Controlling the fuel delivery under steady state conditions where the RPM and throttle position are constant is a relatively easy task. When sharp changes in throttle position are made, however, this can result in a momentary lean condition when the throttle is opened and a momentary rich condition when the throttle is closed. These conditions, when the driver is quickly changing throttle position, are known as transient conditions. You may also hear them referred to as accel enrichment, decel enleanment, or tip-in enrichment. Normally, these transient conditions are dealt with in the ECU by way of tables that will modify the fuel delivery based on the rate of change of throttle position and the current engine RPM. While this is an effective way of getting good control over the air-fuel ratio and preventing the engine from hesitating when the throttle is opened sharply, in this module we're going to discuss what exactly is going on inside the engine, as well as why these transient fueling changes are needed in the first place. Let's start with a simple analogy. First, let's take a normal kitchen chopping board and hold it on a 45-degree angle into a sink. Now we can take a spray bottle filled with water and spray it against the chopping board. If we spray repeatedly, we'd see that for the first 2 or 3 sprays, no water actually drips off the chopping board. Instead, the water is forming a surface film on the chopping board. If we keep spraying though, eventually the pool gets large enough that the water will start dripping off the end of the chopping board and into the sink. From this point on, each time we spray the board, water will immediately drip off it. This is similar to what's happening inside the engine when the injectors are spraying fuel against the port wall. Under steady state operation, a portion of the fuel delivered by the injector will form a puddle or film of fuel on the intake port wall. The size of this fuel film will be affected by numerous aspects like the injector placement, port wall temperature, air pressure, airspeed and injection volume. The fuel film will build up to a certain level and then will begin to evaporate off. Some of the fuel film will also end up entering the cylinder in the form of liquid droplets. Under steady state conditions, this fuel film is topped up by the injector at the same rate it evaporates, so the volume of the fuel film stays constant. As I've mentioned, the volume of the fuel film depends on many parameters. Some of them, like the injector placement and spray pattern, don't tend to change much and remain constant. Others, such as port temperature and air temperature, tend to change quite slowly and again don't have a considerable impact on the running of the engine. Airspeed and pressure, however, can change very rapidly, and these can have a large influence over the volume of the fuel film. This can cause the lean mixture we see when the throttle is open quickly. Let's see why this is the case. The biggest influence over the volume of the fuel film is manifold pressure, and this is affected dramatically by changes in throttle position. Under low manifold pressure, the volume of the fuel film will be lower, and under high manifold pressure, the volume of the fuel film will increase. The problem is that the volume of the fuel film tends to take some time to build up though, so when the manifold pressure moves quickly from low to high, there'll be a period of time, usually in the order of a few tenths of a second, during which the fuel film volume increases. When this is happening, a portion of the fuel injection pulse is being used to increase the volume of the fuel film, and hence it isn't making it into the engine. Once steady state conditions are again established at the new manifold pressure, the volume of the fuel film will have stabilized and the fuel delivery to the engine is again correct. It's during these periods when the fuel film volume is increasing or decreasing that this means the fuel delivery reaching the engine cylinder will be incorrect. Let's look at an example where the engine is being tuned correctly in steady state conditions at 2000 RPM at 2 points in the efficiency table, 40 and 80 kPa. In both sites, the efficiency table has been correctly calibrated to achieve a lambda value of 0.90. At 40 kPa, we find that this requires an injector pulse width of 3 milliseconds, and at 80 kPa, it requires a pulse width of 6 milliseconds. Let's assume, however, that at 40 kPa, 2.5 milliseconds of the injector pulse width is making it directly into the cylinder, and the other 0.5 is topping up the fuel film. Of course, the film is evaporating at the same rate it's being topped up, so the cylinder is still receiving the required 3 milliseconds of overall fuel delivery. At 80 kPa, 4.5 milliseconds of the injector pulse width is delivered directly to the cylinder, and 1.5 milliseconds tops up the fuel film. The fuel film in this case has grown by the equivalent of 1 millisecond. Again, under steady state conditions, this doesn't matter as the fuel evaporates off the fuel film at the same rate it's topped up. The problem occurs though when the throttle is snapped open rapidly and the manifold pressure moves quickly from 40 to 80 kPa. In this instance, 1 millisecond of the delivered fuel pulse width will go to increasing the size of the fuel film. The engine will therefore run lean momentarily while the fuel film builds up and reaches equilibrium again. When we close the throttle sharply, we see the exact opposite effect as the fuel film is reduced and hence the engine will run rich momentarily as the fuel film is depleted and reaches equilibrium again. While the majority of ECUs deal with these transient conditions based off the rate of change of throttle position, it's not strictly this rate of change that affects the engine's requirements for additional fuel, but rather the change in manifold pressure. Modelling transient enrichment off change in TPS, however, is effective in most instances and is relatively easy to both understand and tune. Keep in mind that in some OE ECUs, as well as a handful of aftermarket ECUs, transient enrichment is handled by properly modelling the fuel volume that's deposited on the port wall and how this fuel volume will change with manifold pressure and RPM. In summary, transient conditions, also known as accel enrichment, decel enleanment, or tip-in enrichment, are when the throttle position sees sharp changes. ECUs are able to deal with this using tables, preventing a stumble on snap acceleration or a big overfuel condition if the throttle is rapidly lifted. As always, properly understanding what's going on inside the engine will allow us to do a better job of understanding why these transient compensations are required, and that lets us do a better job of tuning the engine.